Good morning, everybody.
Good morning.
Good morning, sir.
Good morning, sir.
Title slide.
Yes, sir.
And can you see the change in the slide now? 1 minute, let me. Can you see the change in the slideshow? Hello?
Sir, actually, we are able to see only the folders part, sir. Slides are not visible.
Let me go out and come again. No, there will be a problem. Can you see the slide now?
Yes, sir.
Yes, sir. Yes.
Let me change it. Please tell me whether you can see the change in slides.
Yes, sir. It is visible. Like slides are changing.
And please also tell me whether it is being recorded or not.
Yes, sir. It is recorded.
It is being recorded, right? Hello?
Yes, sir. It is recorded.
Yes, sir.
Thank you. So the new chapter is defects in crystalline materials and how to make the material strong, strengthening mechanism. In this chapter, we are going to address few things. First is why theoretical shear strength of a material is about 500 times higher than the strongest material known to humankind. In first year, you did mechanics. Okay. There, the theoretical shear strength is used to calculate to solve various problems. And that mechanics is called continuum mechanics. You never ever were introduced to the fact that materials, as a piece of steel, aluminium, or anything you use, has defects in the microscopic range. But in real material, when you try to solve problem, you see their strength is much, much lower than theoretical shear strength. So the points we are going to address include how strength and dislocation motions are related. Okay, and what is dislocation that we are going to talk about? How do we increase the strength of a material? A given material, I cannot change its composition, but how will I process it so that its strength will be much higher? And how heating can change the strength and other properties of materials. These are some of the important features you are going to learn in this chapter. Now, if you look at it in the next chapter, when I teach you, I'll talk about solidification. How from a molten bath, solid metal or alloys form. But just for the sake of this class, you see, you have a volume of molten liquid. I am cooling it below its melting point or freezing point, and tiny solid nuclei formed in the molten bath. These are the solid nuclei, and the rest of the bath is molten metal. With time and undercooling means you are cooling below the freezing point, these tiny nuclei grow, and these are called crystals are growing. How much they grow? They keep on growing until they meet another growing crystals. Until they meet another growing crystal, because one solid will not penetrate into another solid. This is how growth takes place. And eventually you get a structure like that. And is the grain structure which was introduced to you in the lab class yesterday. So each grain is a single crystal, and each of them has an orientation of grains. Say atoms are orientation of atoms. Atoms are arranged in a particular fashion. Same crystal structure, but atoms will be arranged in a different orientation. Different orientation. Same crystal structure, different orientation. So the grains having in a single phase material, the grains having the same crystal structure, but their orientation of various crystallographic planes containing atoms are different from one grain to another grain. So there is a boundary between the grains. These are the boundary between the grain, and they are called grain boundaries. Grain boundaries. And this is the structure. There is a grain boundary here. And everywhere I see a grain boundary here in a structure. But if the material consists of one single grain, a large material, just like the turbine blade of a jet engine, then it is called a single crystal. So here you can see better. The grains are oriented, or the crystallographic plane in this grain. The atoms are oriented, or crystallographic planes are oriented in a particular fashion in this material. However, they are oriented, this plane, in a slightly different fashion, but they having the same crystal structure. Okay, same crystal structure. So this is my grain boundary. This is my grain boundary. So grain boundaries are the regions between the crystals or grains. Each grain is a single crystal. Transition from lattice of one region to that of other crystal structure does not change. Only the orientation changes. And the grain boundary area is slightly disordered. If I grow big grains in the lab class, we used to do that. We will show you with a naked eye. You can see these large grains. Most grains we see with an optical microscope. But if you allow a slow cooling, we grow a very large grain, and they can be seen with your naked eye. And These grains can be equiaxed toward the center of this ingot or can be elongated near the boundaries of the mold in which they were solidified. So what is an imperfection in a solid? There is no such thing as a perfect crystal. We talked about a perfect crystal, we talked about Bravais lattices, all the atoms are occupying in their assigned position. But in reality, hardly anything has a perfect structure. And what do we mean by these imperfections? That we are going to address here, and why they are important for us. So many of the important properties of materials are due to the presence of imperfections in a solid, imperfections in the atomic level. It can be a missing atom from its lattice site, it can be an impurity atom in the lattice site, and many other things which will come across through this course of this chapter. Any question?
Sir, can you please explain the angle? Boundary
Angle means, you see, the atoms are arranged in a particular fashion. Same crystal structure, look at the square array. Assume square array of atoms for sake of simplicity. Here we also get the square array. But you see the squares are arranged in a particular fashion here. But here they are tilted. So the orientation of the atoms in this grain, grain number 1, is different than the orientation of the atoms in grain number 2. And similarly, here orientation is again different. So this grain number 3 is arranged in a different way. Same crystal structure. So the boundaries between this grain number 1 and grain number 2 and grain number 3, these boundaries arise, this is the boundary, because of orientation difference between one grain to another grain. And this is called a grain boundary.
Yes, I got it.
Sir,
Yes?
sir, how are the nucleons growing to form a big grain, sir?
When you that will be taught in details in the next chapter. For the time being, in a liquid, by statistical fluctuation, suddenly few atoms of the liquid momentarily takes the orientation of the corresponding solid. Momentarily means for a fraction of a second. And then they move away. But if I cool it sufficiently, the metal below the freezing point, that localized region where few atoms took the orientation of the corresponding solid becomes stable. That is called a nucleus. With continued cooling, atoms from the liquid get attached to that tiny nuclei, solid nuclei, and they keep on growing. This is how the solid nuclei grow into grains.
Yes, sir, got it. Thanks.
Now the atomic level or microscopic level imperfections in a material are classified in 3 major groups: point defects, line defects, area or surface defects. Area or surface defects. Point defects can be a vacancy atoms. Means one of the lattice sites where the atom is supposed to be present, it is absent. That is called a vacancy atoms. You remember at the end of the crystal structure, we talked about interstitial sites, octahedral, tetrahedral, and in steel I mentioned in iron. So one out of 500 unit cells may have one side occupied Which side? An interstitial side by a carbon atom. So this is an interstitial atom, which is also a point defect. Substitutional atoms. Say I am making an alloy between copper and nickel. I had pure copper, I added nickel. So some of the copper atom positions will be occupied by nickel atom. And that's the defect. And because the definition of a lattice will be violated. And so a substitutional atom will be a point defect. And why it is called point defects? Because this defect, whether it's a missing atom, an impurity atom like substitutional atom, or an interstitial atom, this defect is in the vicinity of only few atoms. Is a localized lattice disturbance. Localized lattice disturbance in the vicinity of few atoms. Only few atoms. Hence it is called a point defect. Whereas dislocations are called line defects. They propagate in a crystal like a line. Hence they are called line defect. And certain defects exist on surfaces. They are surfaces like grain boundary. We will talk about twin. We talk about stacking fault. These are the surface defects or area defects. Stacking faults. Now, what is a point defect? Please switch off your microphone because the noise is coming. Some construction is going on. Please mute yourself. Point defects. I said a vacancy, a missing atoms. This defect is localized in the vicinity of only few atoms. It's a point defect. An interstitial is a point defect. An impurity atom is a point defect. You see, because it violates the definition of a lattice, point lattice. Now look at the point, a vacancy. How much vacant sites are present in a material? This is the equation. Small n in the number of vacant sites. When in a given volume, how many sites are vacant? Capital N in the total number of sites in that volume. Exponential power minus e to the power suffix s by kT. Es is the energy required to move an atom from the interior of a crystal to its surface. Energy required to move an atom from the interior of a crystal to its surface. That is E suffix s. And K is the Boltzmann constant and T is the temperature in absolute scale. So if I consider the value of Es is approximately 1 electron volt. 1 electron volt. I can get at say 500 degrees Celsius this fraction, this value, approximate fraction of vacant lattice site is 10 to the power minus 10. At 1000 degrees Celsius is 10 to the power minus 5. 2000 degrees Celsius 10 to the power minus 3. You see how much vacancies will be present, how many vacant sites will be present with the increase in temperature. There's huge
Hello,
number.
sir.
Yes.
So, if you won't mind, can you explain that ES thing? Your voice got broken for me.
Let me finish and then you please ask this section. ES is the energy required to move a single atom from the interior of a crystal to its surface. If I have an atom here, interior of a crystal, energy required to move it out and put it on the top surface. This is ES. Okay, energy required to move a single atom from the interior of a crystal to its surface. Clear?
Yes, sir.
So, you see the fraction of the vacant sites increases exponentially. This is an exponential term, exponentially, as a function of temperature. ES is constant for a given material. Boltzmann constant is a constant. So what is the variable? Variable is the temperature. So this ratio, fraction of a vacant lattice site, is an exponential function of temperature. Higher is the temperature, more and more vacant sites we get. At 500 degrees Celsius, I have 10 to the power minus 10, this fraction of a vacant sites. Whereas in 1000 degree, 10 to the power minus 5 order of magnitude. Remember, whatever value you put, this is 1 order of magnitude. You put 2 here, it's called 2 order of magnitude. You put 5 here, it is called 5 order of magnitude. Those power 10 to the power, that value is called an order of magnitude. So there is a change in 5 order of magnitude by the change in temperature from 500 to 1000 degrees Celsius, 10 to the power minus 10 to 10 to the power minus 5. And this is the equilibrium number of vacancies. This is the equilibrium number of fraction of vacant sites. Equilibrium at a particular temperature. In engineering or science, there are two important functions. One is the linear function, the other one is the exponential function. You see, any rate processes, any transformation is the linear function of time. Linear function of time. However, that is an exponential function of temperature. So you want to make a change in a system, you keep it for a long period of time, it will change. But if you increase the temperature by a minute amount, there will be a significant change in the rate. So, any transformation is the linear function of time, but an exponential function of temperature. Any question?
Sir, hello. Sir, the ES value, will it differ for atom to atom, or you have just assumed it?
Some elements, but approximately you can assume is 1 electron volt.
Sure, sir. Thank you.
It varies from atom, from element to element. So what happens when you have a defects? You see, this is the vacant site, and it is localized in the immediate vicinity of only few atoms. So the lattice around it, the atoms around it will try to collapse, and that distorts the plane, distortion of plane, or distortion of the lattice in the localized region. That increases the stress value of the system, and strain is generated in this process. Just opposite it, an interstitial. Self-interstitial means same material. It happens quite often. If you have a material in a nuclear reactor, your highly energetic particles are bombarding it. So the self-interstitial defects can generate in a nuclear reactor. And you see one additional atom is distorting the lattice. Here the lattice is trying to collapse, here it is trying to expand. So any defects, point defects, will introduce a strain in the system, which in turn will introduce the stress level and finally the energy level of the system. And this is one of the calculation for vacancy concentration calculation. And this is from your Callister book. You can look it up how they have done that. You see the value they put is 0.9 EV. I said approximately 1 EV. They put it for copper. This is how they calculate it. You can check these calculations by yourself. Now, what do we said? Summary: a vacant site, an interstitial sites, a large interstitial. What happens? But these two defects I shall not cover because it is taught in our high school. One is Frankel defect and the other one is Schottky defect. That you know from your high school days. Okay. The same thing I showed you. Substitutional solid solution, again another slide. An interstitial solid solution. Substitution like copper in nickel or nickel in copper. An interstitial is carbon in iron making a steel. Okay. Yesterday, Professor Mandal, when he was talking small phase, second phase precipitate. Okay. You look at an aluminium body of a plane or the aluminium utensils you have at home. It is basically aluminium copper alloys, 4.5% copper in it is called duralumin. Plain body also has few other alloying elements. So if you control way, you heat it and cool it, it forms fine second phase particles. They are called precipitates. That gives the strength to this material. I will not go through it, and these interstitial sites I have already covered in crystal structure. This defect. So this all you learned, the Schottky and all these defect. I will not explain this, that you read it up any book, including the textbook. This additional slides I showed it. These two defects you know. What is a Frankel defects and what is a Schottky defect. Please read it up any book. Your class 11-12 book or Callister's book or Shackelford's book. These are, you can recapitulate what was taught there. Now, I mentioned any questions so far?
So could you please explain precipitates again?
Precipitates are thermodynamically a defined phase. If you do certain thermal, this will be taught in details later on, not right now, because I need to teach phase diagram and after that it will be taught. So after 2 more chapters it will come slowly. But for the time being, you do certain thermal treatment in an alloy, and that alloy, in that alloy during thermal treatment, a tiny second thermodynamic phase forms. And why they are tiny, it will be taught later, and if they are very large, it will ruin the properties. That we'll learn in this chapter. So these second phase particles strengthen the material. Whether you say aluminium pots and pans at home or an aluminium body of a fighter plane or a commercial jet engine, say jet planes, they are aluminium alloys and they have fine precipitates. And you learn in this chapter the movement of dislocation gives ductility to the material. So if you hinder the movement of dislocation in a material, you can increase its strength, and this fine precipitate hinders the motion of the dislocation. Thus it increases the strength of the material. So this will be taught gradually starting from this semester. So for the time being, you form by certain thermal treatment a second thermodynamic phase, which are very small in volume, in a matrix of the parent phase, which improves certain mechanical properties like strength. Am I clear up to this point to you?
Yes, sir. Thank you.
Okay. Any other question? How many of you play cards?
Yes, sir.
Yes,
Are you good? Because if it is a physical classroom, I would have showed you. Can you do a good shuffling of a deck of cards?
Yeah. Yes, sir. Can.
Okay. So what type of card games you play? Bridge?
Yes, sir.
Okay. How good are you?
Just means medium, you can say.
How long have you been playing?
How for 3 years?
Okay, is that you are the only person out of 72 who plays card in this class?
Sir,
I
I
don't
play
know.
bluff.
Class.
Yes, sir.
Hopefully you will not try on me. So there are 52 cards in a deck of card, right?
Yes, sir.
You forgot.
No, sir.
You take a deck of card and try to press from one end. What happens? The deck gets
So the
distorted and
distort.
elongated,
Yes, sir.
right? So assume I have a face center, that deck of card is face centered cubic, and each piece of card is in 1-1-1 plane. Okay? Assume each card is a 1-1-1 plane. So I have 52 parallel 1-1-1-1 planes, right?
Yes, sir.
How many of you are still awake in the class?
Yeah. Yes,
Yes,
sir.
sir.
Yes,
Yes,
sir.
sir.
Sometimes
Yes,
you
sir.
will
Yes, sir.
Yes,
yes,
sir, we are
no,
awake.
something you say, otherwise I'll fall asleep. Okay? Then responsibility is yours. You have to teach yourself the class. So keep me awake, please. So assume this is a deck of card. One card, another card, and there will be 50 more cards below it, each card. So if I apply a shear stress from this side, what happens? One card will be gliding over the other card. Yes or no?
Yes, sir.
Yes, sir.
So in middle, this is a 1-1-1 plane. I am looking from the edge of that plane. 1-1-1 plane. Another 1-1-1 planar line. You see the distance of separation between two 1-1-1 planes is A. And the distance of separation between the atoms along the 1-1-0 direction, let's assume this is 1-1-0 direction, is B. And what is X? If I move the first deck of card over the second card, a little bit of movement, this is called an amount X. So this, if I applying a shear stress tau, and tau m is the maximum shear stress, and I get a relationship sine 2 pi x by b. What type of relationship is this?
Sinusoidal.
Sinusoidal
Sinusoidal.
relationship. So it will be like this. A sine curve. It has a peak, it has a valley, it has a peak, it has a valley. That is the wavelength. This is the amplitude. And this is the amplitude is the tau max. And tau is the shear stress. What is x? The slide displacement, the amount by which card number 1 was glided over the card number 2, glided. Okay. So if the displacement amount is very, very small, Hooke's law can be written as tau is equal to G gamma. G is the shear modulus. And what I can write about gamma is x divided by a for a very small amount of displacement. Hooke's law becomes tau is equal to G gamma, and instead of gamma I can write Gx by a. So I get this sinusoidal relationship and another relationship tau is equal to Gx by a. Now the equation 1. If x by b, this x by b is very small, If it is very small, sine 2 pi x by b is more or less same as 2 pi xb. If the x by v value is very, very small, sine 2 pi x by b can be written as simply 2 pi x by b.
Yes, sir. Yes.
Okay.
Yes, sir.
So what I wrote from equation number 1, tau is equal to tau max 2 pi x by b. This is equation number 3. Now combining the equation number 2 and equation number 3, what do I get? Tau max is equal to g by 2 pi and here b by a. And for most metallic crystals, b and a values are more or less same, 2-3 angstrom or so. So I can write b equals to a, so it becomes unit, this one. So what relationship I get then? Tau max equals to g by 2 pi. b by a becomes unity. And this is the theoretical shear strength which you learn from your mechanics class. This is your theoretical shear strength value. The shear modulus, G, for most metals varies from 20 to 150 gigapascal. 20 to 150 gigapascal. However, the tau max is more or less 3 to 30 gigapascal. You see the difference? So actual shear stress required to cause plastic deformation in metallic single crystal is approximately 0.5 to 10 megapascal. What is plastic deformation? You know Hooke's law. Yield strength, up to the yield strength. If you load it, remove the load, you'll get back the original shape and size. Beyond yield point, if you stretch it, remove the load, you'll get the elastic portion back, but certain amount of permanent deformation is there. That is called plastic deformation. Elastic deformation, beyond the yield point, if you stretch it, you will have elastic plus plastic deformation. If you remove the load, elastic portion is recovered, but not the plastic portion. So from this derivation, you see the theoretical shear strength of a material can be as high as 500 times more than the strongest possible material known to mankind. So there must be something wrong somewhere, for which all real materials are having such a low strength, shear modulus, compared to theoretical shear strength, compared to the theoretical shear strength value, which I calculate. During this calculation, what happened? There was a bond between the atoms. When I am gliding one atom of the another, I am breaking this bond. I'm breaking this bond. I'm breaking this bond. And to move one plane of atoms over the another plane, the bonds between the atoms on the top layer compared to the atoms just sitting below in the bottom layer, each bond has to be ruptured at the same time, so that the first layer of atom will glide over the second layer of atom. Any question?
That 2 pi x by v, that sinusoidal behavior, it is we are applying that or we have derived it from somewhere?
Sorry, please say it slowly. I couldn't understand your voice. Say it again.
So that sinusoidal behavior, it is given, like we are applying that stress or we have derived it from somewhere?
It's a theoretical derivation.
Okay.
You must have a copy of Dieter's book, chapter 4, 5, and 6. I am following. Chapter 4, 5, and 6 is being followed from today. So George E. Dieter, Mechanical Metallurgy book. Any question? Now, to explain this discrepancy, why theoretical shear strength is so high, in 1940s, mostly physicists and mathematicians were coming up with the concept of dislocation in a crystalline solid. Dislocations. In 70s, when transmission electron microscope development became quite mature, we saw those defects. So the theories which will be taught, including one thing when I will teach, remember, it's called Bodin-Herring source in dislocation theory, is the same John Bodin who won 2 Nobel Prizes, one for discovery of transistor, the other for superconductivity theory, BCS theory. That is his work. So in 40s, the physicists and mathematicians were developing concepts of dislocation. Nobody ever seen that. After 30 plus years, first evidence we saw. And then in last 30, 40 years, we have seen so many things. But very interesting thing, all the theories which were developed by the sheer power of mathematics have been proved correct. Every theory of dislocation have been proved correct. And you can experimentally observe those. So in the transmission electron micrograph, you saw a bright matrix, and you see these black lines here, black lines. All these black lines, I'm coloring only few. These are defects called dislocations, which we will explain shortly. A dislocation is called a region of localized lattice disturbance separating a slipped region of a crystal from yet to be slipped region. Let me repeat. A dislocation is called a region of localized lattice disturbance separating a slipped region of a crystal from yet to be slipped or unslipped region of a crystal. Consider the deck of cards, one card. There is a line, hatch line, above which the card, by the application of shear stress, above which another card, it moved from left to right. The green portion above which the card of the crystal moved, say by 1 atom spacing, and the red portion is yet to be moved. This line AB, this line AB is the region of localized lattice disturbance separating a slip region. Slip means on a rainy day in a wet floor, you can glide on it. That's a slip on which the crystal moved, above which. This is the slip region. It is unslipped or yet to be slipped. So region of localized lattice disturbance separating a slipped region from the yet to be slipped region. So this line AB is called a dislocation. Now the next question is, why I am calling it a region of localized lattice disturbance? Here at the top of the C region, all the atoms moved by 1 atomic distance. You see in a march past in your NCC class or in school you did, if every person moves forward but one leg length, one step, the formation remains unchanged. You see the Republic Day parade. Everybody is marching one step ahead. the formation of those people in the parade are same. But if one person moves a slightly less than each step, the formation will be disturbed. So every atom at the top of C moved by one atom spacing. The crystal structure is unchanged because they move by one spacing. D is yet to be moved. The region AB, this line has a finite width. It can be 10 angstrom to 20 angstrom width, let's for example. And it is called a region of localized lattice disturbance. Localized lattice disturbance. Because in this region, which I will show, atoms move by a distance which is not equal to one atom spacing, rather a fraction of an atomic spacing. So that region is disturbed. So dislocation is a region of localized lattice disturbance separating a slip region from yet to be slip region. Any question? In the bottom figure, assume a block of butter. You take an Amul butter, 500 grams slabs, take a hot knife, pass the knife through this piece of butter along the plane A, B, C, D. Make a thin cut. And from right to left, with your thumb, press it from right to left. You move the portion of the top portion of the butter with respect to the bottom portion by this amount. Which amount? It's this amount. And the surface A, B, C, D, above which top portion moved with respect to the bottom portion. So what I should see here, this is the region A, B, C, D in this drawing. And the line AD is the line separating the slip region from the yet to be slip region at your left. So AD is the region of localized lattice disturbance separating a slip region from yet to be slip region. Okay. Any question? This is the picture, other way to look at it. This region. This is the plane on which you move the crystal. Right side, this gray hatch region, bluish hatch region is the slip region, and left side is yet to be hatched. Now I will not start the next slides, but I just want to point it out. This is an AD line separating the slip region from the yet to be slip region. So if I take a plan view of the line AD, or H view, means here, this plane, if I looked at it, that is the plane here. This region will appear like this. This entire region, if I take a look at this from this side, if I take a look from this side, in atomic level, it will appear like this. One half plane and remaining planes are continuous. I shall not start from here today. I shall start it tomorrow. If you have any question, please feel free to ask me now.
So this
Any
view is the side view, right?
end view or side view. Of that plane AD, the region of localized lattice disturbance separating the slip region from yet to be slip region. You see why I'm calling the region of localized lattice disturbance. Instead of a continuous plane, you have a half plane. And each plane is distorted here. The amount of distortion is more if the plane is nearer to the extra half plane, this extra half plane. Further away you get from this extra half plane, the amount of distortion of the plane, means how much it got bent, will be less. So beyond certain distance, the planes will not be bent anymore. So that line AD, dislocation line, has a finite width. And in that line, the atoms lying there, same crystal structure, but the lattice is distorted. You see by schematic diagram. The lattice got distorted from its equilibrium position. And the dislocations where they have the extra half plane, that type of dislocation is called an edge dislocation. If you look from the top, it appears like an edge of a knife. So the name edge dislocation came. I shall continue from next class this portion. Any question? Anybody has any query?
Sir, in this image, where is the slip region?
This is the plane. I am looking at only this region. Only few atoms thick in this region along this line. How do they look like? I am looking from this arrow, this line, this plane, bold plane. How do they look like? This is what we are looking at.
Okay, sir.
Look at the book, please, tonight. So if you do not have any question, let me take the attendance.